Greetings and welcome. Subscribe the YouTube channel Thermal Engineering for video sessions. This is video session on overall heat transfer coefficient in heat exchanger. In this session, you will be able to explain overall heat transfer coefficient in heat exchanger. Let us discuss about need of overall heat transfer coefficient. For designing or predicting the performance of a heat exchanger, it is necessary to study governing parameters such as overall heat transfer coefficient, that is U, due to various modes of heat transfer, means say conduction, convection, total surface area of heat transfer, means A, and inlet outlet fluid temperatures. Here in this diagram, overall energy balance in a heat exchanger is shown. Hot fluid is passing through this upper passage and cold fluid is passing through this lower passage. So here is a heat transfer taking place from hot fluid to cold fluid. Because of heat transfer, the inlet outlet temperatures of these two fluids are changing. Inlet outlet temperature of hot fluids are TH1 and TH2, and for cold fluid TC1 and TC2 respectively. Theta 1 is a temperature difference at the inlet of heat exchanger between hot fluid and cold fluid. Theta 2 is a temperature difference between hot and cold fluid at the outlet of heat exchanger. This is the heat transfer area interface across which heat transfer takes place from hot fluid to cold fluid. Here m dot is a mass flow rate taken into kilogram per second. Cp is a specific heat of fluid at constant pressure. Delta T is a temperature drop or rise of a fluid across the heat exchanger. Neglecting the energy losses from the heat exchanger to atmosphere, it can be written energy given by hot fluid is equal to energy received by the cold fluid. So mathematically, mCp delta T product for hot fluid is equal to mCp delta T product for cold fluid. So mCp delta T is a total heat content or heat transfer which is taking place from the hot fluid to cold fluid. It can be elaborated as mCp means mass into specific heat product for hot fluid into temperature difference between inlet and outlet of hot fluid is equal to mCp product for cold fluid into temperature difference between outlet and inlet of cold fluid line. The total heat transfer rate in the heat exchanger is given by the formula Q is equal to U into A into theta m, where U is overall heat transfer coefficient between two fluids. This is taken into consideration because whenever there are different modes of heat transfer are coming into picture, A is a total surface area of heat exchanger of heat transfer, and theta m is a logarithmic mean temperature difference, means LMTD. There will be separate video for the LMTD. Now we will have two cases for the overall heat transfer coefficient. First case is for plain wall and second case is for shell and tube type heat exchanger. So overall heat transfer coefficient in case of plain wall, here this is a plain wall which is shown. It is exposed to hot fluid on one side and cold fluid is on other side of the wall. Hi and Ho are the convective heat transfer coefficient of the fluid on hot side and cold side. K is the thermal conductivity of wall material. L is the thickness of wall, means dimension. Q is a heat transfer taking place across this wall from hot fluid to cold fluid side. Now here these are the three thermal resistances which are shown. This is a thermal resistance diagram. So here first resistance Ri, that is taking place on the hot fluid side due to convection heat transfer between hot fluid and left side surface of the wall. So here is a temperature difference Ti and T1. Across this heat transfer take place. So thermal resistance is given 1 upon Hi into A. R1 is a thermal resistance for the wall where the heat transfer take place by conduction. So for the conduction, formula is L by Ka, where L is the length, here it is taken as thickness, and Ro is a thermal resistance for the outside fluid, cold fluid, for convection heat transfer, which is given as 1 upon Ho into A. In all these three formulae, area is common to all, that is A. Now here total thermal resistance will be summation of these three, means Ri plus R1 plus Ro. Now we know that overall heat transfer coefficient we can find by using the formula. So for that we can take first of all basic relation, that is Q is equal to delta T upon summation of resistances. Delta T is a temperature difference between hot fluid and cold fluid. So hot fluid temperature is Ti, cold fluid temperature is To, which is shown here in the figure, divided by summation of R. This sum of resistances already taken from this last slide. So we will say this to our equation number 1 and 2. Then as Q is equal to, in another way it can be written as U into A into delta T, means UA into Ti minus To, say equation number 3. Comparing equation 2 and 3, means here LSH means left hand side is a Q, so we can write right hand side as here UA Ti minus To, this will be here, and this expression will be here. Now in this case here 1 upon A can be taken common from this bracket. So here this Ti minus To bracket, left side and right side both will be cancelled. This area and this 1 by A will also get cancelled. So here total or overall heat transfer coefficient for the plain wall equation we will find, that is what, 1 upon bracket 1 upon Hi plus L by K plus 1 upon Ho. This is the second case, overall heat transfer coefficient in case of shell and tube heat exchanger. This is a diagram where we see this is a tube side hot fluid is flowing and shell side cold fluid is flowing. there is a heat transfer between these two fluids. Here the hot fluid is passing through the tube. Its inner surface is at radius R1 and outer surface is at radius R2. So here heat transfer is taking place in radial direction, means along the radius, from hot fluid to inner wall of tube, means here by the convection. Then through this wall heat transfer take place by conduction, and finally from the outer surface or outside surface area of the tube to the cold fluid by convection. So here heat transfer is taking place in 3 steps. So here these 3 heat transfer modes are shown: convection, conduction, convection. Thus here 3 thermal resistances come into picture. So first thermal resistance is between inside fluid temperature and inner surface wall temperature T1, that is Ri for the convection. Its formula 1 upon Hi Ai. Second thermal resistance is for wall R1. Its formula is natural log R2 by R1, means its outer radius and inner radius of the tube ratio, divided by 2 pi KL. K is a thermal conductivity of tube wall material. L is a length of tube. Here the temperature difference is T2 and T1. T1 is a inner surface temperature of the tube and T2 is outside surface or outer surface tube temperature. Third resistance is for the cold fluid which is passing on shell side. So here it is given as 1 upon HOAO, where HO is a convective transfer coefficient for outside fluid, means cold fluid, and AO is a outer surface area of the tube. Now the surface area inner tube is given as a 2 pi r 1L, because circumference 2 pi r into length of tube, that is area, surface area, inner surface area AI. Similarly AO means this outer surface area, black circle, it is 2 pi r2 into L. Now total thermal resistance will be summation of these 3 resistances, means summation of these 3 formulae in the form of area formula. Here 1 upon area AI is 2 pi r1 into Hi plus natural log r2 by r1 divided by 2 pi KL. This is term as it is, and here 1 upon HO multiplied by AO area is 2 pi r2, surface area, outer surface area of the tube. Now we have Q is equal to delta T upon sigma R, or summation of R. This is standard equation, already we have seen. Say equation number 1. Again we can write Q is equal to UA delta T. Now this equation we can write for the overall heat transfer coefficient based on inner surface area, means UI into inner surface area AI into corresponding temperature difference is equal to, this is overall heat transfer coefficient based on outer surface area of the tube, UO into outer surface area AO into delta T. So comparing equation 1 and 2, this left hand side is the same, so equating right side means delta T upon summation of R is equal to these two expressions. Now here in this equation, delta T can be cancelled because it is present in all the expressions. Remaining terms we will write. Further, taking reciprocal of this equation, we will have here summation of R is equal to 1 upon UIAI is equal to 1 upon UOAO. Now we will have separate equation for overall heat transfer coefficient based on outer surface area of the tube, which can be expressed as UO. So how to obtain it? See here, this UO we will take on the left side and this summation R we will take on the right side. So what will happen? UO will be equal to 1 upon AO into summation of R. Now summation of R already we have from the last slide or from the diagram. Outside the bracket AO is written. Next step, we can multiply this AO with each term inside the bracket. So let us do that. So UO is equal to 1 upon, multiplying inside first term, it comes AO upon AI HI plus AO upon 2 pi KL natural log of R2 by R1 plus here, if you see in last expression here, this AO, if you multiply to this last term, AO and this AO means numerator denominator will get cancelled. Thus, here 1 upon HO will remain. So this is a overall heat transfer coefficient formula based on outer surface area of the tube. Now, overall heat transfer coefficient based on inner surface area of the tube can be expressed as in the same way. So for that, we can have UI is equal to 1 upon AI summation of R. Summation of R is a bracket term. Now multiplying this AI with each term. So here multiplying to this first term, this AI will get cancelled. So here 1 upon HI remains. Next, AI multiplied by this second term, natural log of R2 by R1 divided by 2 pi KL plus AI divided by AOHO. So this is the formula for overall heat transfer coefficient based on inner surface area of the tube. So at the end of this session, you can explain overall heat transfer coefficient in heat exchanger. So subscribe the channel Thermal Engineering for video sessions. Thank you.